In this module on econometrics, we will study a very important topic known as the goodness of fit. With the help of data, we estimate the postulated model. After estimation, naturally the question arises, how good is our model? So, that is the topic we will take up today. In other words, we will look at the goodness of fit of an estimated model. Let us consider the following linear regression model. As you can see, this is our familiar k variable linear regression model, and we assume that it follows the classical properties of zero mean, constant variance, homoscedasticity and no autocorrelation. Also, we assume that there is no perfect multicollinearity in the model, which makes the model estimable using ordinary least squares method. So, the estimated model is written as you can see, each of the parameters is now put with a hat. So, beta 1 hat is the estimate of beta 1, beta 2 hat is the estimate of beta 2, so on and so forth. And as you already know, the random disturbance term cannot be estimated. So, yi is the original or observed value, y hat I is the estimated value. Naturally, there is an error of estimation given as ei equal to yi minus y hat I. So, the question arises, how good is this model? How good is the fitted model? That is basically the topic called goodness of fit. To understand the goodness of fit, first we will focus on a decomposition of the total sum of squares into explained sum of squares and residual sum of squares. We now look at the decomposition of the total sum of squares into explained sum of squares and residual sum of squares. So, our model is written as yi is equal to y hat I plus ei, and in deviation form we write this as yi small letters is equal to y hat I small letters plus ei. The reason is that the mean of observed values and the mean of estimated values are one and the same. This happens due to the first normal equation in a model that has an intercept term. So, now let us look at the sum of the squares of small yi. If we square the right hand side, we will obtain y hat I square plus ei square plus twice y hat I ei, and then we sum. Note that this is the covariance between estimated values and the error, and this estimated y depends on x's, but from the normal equations the covariance between error and x is equal to 0, and therefore, this term is equal to 0. Hence, we write the resulting equation as total sum of squares is equal to explained sum of squares plus residual sum of squares. So, because of the property of the normal equations, the covariance between the error and estimated value is equal to 0. Therefore, we can partition the total sum of squares into explained and unexplained or residual sum of squares. This partitioning of total sum of squares into explained sum of squares and residual sum of squares forms the basis for explaining the goodness of fit. Intuitively, it is easy to see that explained sum of squares forms the strong point of the model. Given the total sum of squares, higher the explained sum of squares, better we would say the model turns out to be. So, the fit of the model depends on the ratio of explained sum of squares to total sum of squares. So, if we divide throughout by total sum of squares, then we write this as TSS by TSS is equal to ESS by TSS plus RSS by TSS, or on the left hand side we get 1, and the ratio of explained sum of squares to total sum of squares is known as the coefficient of determination. The notation is capital R square. Capital R is the multiple correlation coefficient between yi and all the explanatory variables, the set of xi's taken at the same time. So, it is the correlation between y on one hand and all the set of x's on the other hand. The square of that correlation is the square of the multiple correlation, also known as the coefficient of determination, and this is RSS by TSS. So, that means RSS by TSS is nothing but 1 minus R square. So, you can see that higher the value of R square, greater is the proportion of explained variation to total variation, and lower is the proportion of residual variation to total variation. Therefore, R square is often taken as a measure of the goodness of fit of an estimated model. Let us explain the term R square in a little bit greater detail. So, as I just now mentioned, R square is the square of the multiple correlation. So, R is actually written as R, the correlation between y on one hand and x2, x3, x4 up to xk on the other hand. The literature also mentions R as R between y and 2, 3, 4 dot dot k. So, these are different ways of writing R. So, this is the multiple correlation between y on one hand and the entire set of explanatory variables 2 through k, x2 through k, xk on the other hand. Please remember that x1 is the variable associated with the intercept. So, it always takes the value 1. So, we do not write 1 here. So, y dot 2, 3 up to k, and the square of that is the coefficient of determination. The idea is that since y is some function of x2 through xk plus some disturbance term, of course, this is a linear function, linear in the parameters. So, the greater this part is out of the total variation, the better is the model in terms of its ability to explain the variation in yi. And this decomposition gives rise to what we call the analysis of variance. So, we analyze the variance of this model. We will now look at an ANOVA table, which is also known as the table for analysis of variance. Let us now take a look at the ANOVA table, or the table showing analysis of variance. The first column refers to the source of variation. The second column gives the degrees of freedom. The third column gives the sum of squares. The next column gives the mean square. And finally, we calculate an F statistic from these results. So, as we know, there are two sources of variation. The first is the regression. The second source is the residue, and they add up to the total variation. So, as we just now saw, the regression and residue are the two sources of variation, and they add up to the total variation. Before coming to the degrees of freedom, first let us look at the sum of squares. We already know that this is known as the explained sum of squares, and the residual variation is known as the residual sum of squares. They add up to the total sum of squares. Now, let us come to the degrees of freedom, the concept of degrees of freedom. As we know, residual sum of squares is the sum of the squares of the error terms. In order to arrive at this, we had to estimate beta 1 hat, beta 2 hat, right up to beta k hat. So, out of n observations, because the model runs from I runs from 1 to n. So, out of n observations, in order to estimate k parameters, we lose k degrees of freedom, and therefore, we say that the residual variance has n minus k degrees of freedom. The total degrees of freedom in a model with n observations is n minus 1, and therefore, the degrees of freedom associated with explained sum of squares is k minus 1. You can see that n minus k plus k minus 1 is n minus 1. So, to estimate the model, we need to estimate k parameters. Therefore, we lose k degrees of freedom, and we are left with n minus k degrees of freedom when we compute the residual sum of squares. The total sum of squares has n minus 1 degrees of freedom, because given n minus 1 values, the last value is not free to vary, and so the regression sum of squares or explained sum of squares has k minus 1 degrees of freedom. Next, we come to the concept of mean square. Mean square is nothing but the ratio of explained sum of squares to the corresponding degree of freedom, or the ratio of residual sum of squares to its corresponding degree of freedom. So, here we write explained sum of squares divided by k minus 1, and the mean square for the residue is residual sum of squares divided by n minus k. Finally, the ratio of the mean square arising from the regression to the mean square arising from the residue is given as an F distribution. So, this F distribution has k minus 1 and n minus k degrees of freedom. As you know from the statistical preliminaries, the F distribution is a ratio of two independent chi-square distributions, each divided by its respective degree of freedom. So, ESS is a chi-square with k minus 1 degrees of freedom, and RSS is another chi-square independent of ESS, because we have decomposed the total variation into explained and residual sum of squares, and the degrees of freedom associated with residual sum of squares is n minus k. So, this F statistic is given as ESS by k minus 1 divided by RSS by n minus k. It is interesting to look at the F statistic in a greater detail. So, we write F with k minus 1 and n minus k degrees of freedom is equal to ESS by k minus 1 divided by RSS by n minus k. Now, if we divide both the numerator and denominator by TSS, then we can just factor in that TSS and we can obtain this is equal to R square divided by k minus 1 all upon 1 minus R square divided by n minus k. So, the goodness of fit, which is measured by R square, is also reflected by the F statistic. Let us now look at an example of R square. Supposing we have an application where R square between y 2, 3 up to k is equal to 0.723. This means that 72.3% of the total variation in capital Y, that is summation small y I square, is explained by the variation in the x variables, which also means that the residue, that is 0.773 and 780, 27.7% of the variation or variance is unexplained. So, that in a very concrete sense is what we mean by goodness of fit. Naturally, one would like to have as high a value of R square as possible. Now, there is a caution to be taken at this point of time, because as we add new x variables, R square goes on increasing, or at least it does not decrease. It will not decrease, usually it increases. So, there may be a tendency of going on including more and more x variables without any reason. Those variables may not be really relevant, but we can include them just in our bid to increase R square. So, to put a check on that, what we do is we develop the concept of the adjusted R square. So, the adjusted R square is R square modified to take into account that we should not unnecessarily go on adding more and more x variables. So, r square is equal to explained sum of squares by total sum of squares, and that is equal to 1 minus residual sum of squares by total sum of squares, because total sum of squares is a sum of explained and residual sum of squares. Now, as we said, total sum of squares has a degree of freedom n minus 1 and residual sum of squares has the degree of freedom n minus k. So, this is degrees of freedom n minus 1 and that is degrees of freedom n minus k. So, we adjust these residual and total sum of squares by their respective degrees of freedom to arrive at r bar square, which is known as the adjusted r square, and we arrive at 1 minus RSS by n minus k divided by TSS by n minus 1. So, you can see that as we go on increasing the number of x variables, RSS will fall, but at the same time, because we are adding more and more explanatory variables, the degrees of freedom will get lower. So, this adjustment kinds of puts a check and balance on two things. On the one hand, we have a tendency of increasing the number of explanatory variables. On the other hand, we have to take into account that degrees of freedom are accordingly modified. So, this is known as the adjusted r square, and there are various other ways of expressing this adjusted r square, but this is the simplest way. One more thing to take into account or to remember is that sometimes r bar square can be negative. So, it is possible that r bar square can be negative, whereas r square will always be non-negative. R square will always be non-negative, whereas r bar square can sometimes be negative. Another important point that we have to keep in mind is, if we have model 1 and model 2, and if we have r square from the two models, say this is r square from model 1 and this is r square from model 2, then can we automatically compare these two? The answer is, we can compare these two r squares, provided that the explained variable, the y variable, is the same for the two models. Unless the y variables are the same, we cannot compare the two r squares. Reason is very simple. At a fundamental level, conceptually illuminating level, we must understand that r square is nothing but the correlation, it is nothing but the simple correlation between y and y hat. So, r square is nothing but the simple correlation between y and y hat, and supposing we have a model where log of y is beta 1 plus beta 2 x 2 I plus beta 3 x 3 I plus u I, and another model where simply y I is equal to alpha 1 plus alpha 2 z 2 I plus alpha 3 z 3 I plus v I. The structure is the same as in the classical linear regression model, but here the explained variable is log y, whereas here the explained variable is only y. Explanatory variables are also x over here and z here. So, the correlation between log y and estimated log y is not the same as the correlation between y and estimated y. So, the r square that we get from this model and the r square that we get from this model cannot be compared, because this is r square, the correlation between log y and estimated log y. Here it is the correlation between y and estimated y. What we can do is, from here we can take the anti-log and then we can get y I, and y hat I, and then we can compare this with r square from model 2. So, that is r square from model 1. So, we can take the anti-log of this, then compute the correlation, and then only we can compare these two models, and we can perhaps go for the model which is a higher value of r square.